So let's talk about what scatter plots are used for first, okay? What a scatter plot does is it allows you to see if two different things are tied together, if they're affecting each other or not. So for example, here in this example, you've been exercising, and then when you go to the doctor, they say that your resting heart rate is different. So then you start measuring the amount you exercise versus your resting heart rate every week to see if the exercise is changing your resting heart rate. And it's the scatter plot that would allow you to tell for sure if there really was an effect. Okay, so scatter plots are for real world data. With two variables, which are an ordered pair. Okay. The data will not generally fall in a straight line. And this is why they're called scatter plots, is because you plot all the ordered pairs and they make a pattern. But it's not usually, you don't usually get a scatter plot where all of the ordered pairs make a nice perfect straight line. It can happen, but that would be exceedingly rare. Okay, the x value is the independent variable.
Wait, so the first line and the second line, those don't go together?
Huh?
Represents real world data with two variables. Data generally does not form straight
Yeah,
lines.
it's another thought.
Mm-hmm.
This is all part of what a scatter plot is. The x value is the independent variable. The y value is the dependent variable, or rather what you think is the dependent variable. Sometimes the two variables aren't independent on each other. They're completely separate. So, like I said, a scatter plot is used to determine if there is a relationship. Okay, so you can determine if there is a relationship, and then you can use the information to make predictions about data that you don't have. For example, if you're charting things over months and you make all your scatter plot, then you could make a prediction about 7 months from now. Or you could make predictions about time before you were collecting data, like how was it back then, kind of thing. Now, these predictions are not always going to be 100% accurate. If you went back 20 years and you were charting CD sales per month in a scatter plot, and then you were thinking about investing in CD manufacturing, well, you'd be looking at the rise of CD sales as more and more people bought CD players and were buying CDs, right? And so you could predict in 2015, CD sales are going to be through the roof. And then along comes the iPod, and CD sales tank, right? So they're not always 100% accurate because we can make predictions about the future, but we don't know what's going to happen to change the situation for, like the invention of a new technology. But, they're pretty accurately can make short-term predictions. Any questions on what a scatter plot is for? Okay. So here is an example of a scatter plot. As you can see, it doesn't make a straight line. This is prices of peaches versus the number of peaches sold. Over here we have a higher number sold. Over here we have the lower number sold. Up here we have the higher price. And down here we have the lower price. Okay, when we look at this, we can see that when the price is high, we don't have a lot of peaches being sold. So, high price, low sales. And when the price is low, the sales are higher. Okay, so there is a relationship. Okay, and if we look at the dots, the pattern of the dots, you can sort of see how they kind of approximate a line, like they're going, you know, downward in the general vicinity of a line.
So that at first they were a high price.
Yeah. At first the price was really high, but you can see the sales are low. And then down here, when the price gets low, the sales have gotten higher. Okay, so just by plotting these points, you know, if I looked at all the points, like all the prices per the sales, like as ordered pairs, and I just looked at this list of numbers, I wouldn't necessarily be able to just look at it and say, yes, there's a relationship there. But when I put it on a scatter plot and I can see it visually, I can say, oh yeah, look, that is a definite relationship. When the price is lower, the sales are higher.
When the price is lower.
Price is low, sales are high. Right? Because so if we put numbers here, 1, 2, 3, like per pound, you know, I'm just picking fake numbers. Okay, so this is like $8 a pound. This is $1 a pound. Well, when they're $8 a pound, like 1 pound is being sold, or 2 pounds are being sold, or
the Y is the higher number sold.
Yeah.
And the X is
No, the Y is the price. How much it costs per pound.
okay.
And then X is the pounds that are being sold.
So what did you say numbers again?
When the price is high, up here at 8, not a lot is being sold.
Okay.
But when the price is low, over here $1.50, then more of it's being sold. Does that make sense? Because it's cheaper, right? Like, okay, if you went to the grocery store and you were like, ooh, peaches, $8 a pound, you're not going to buy $8 a pound for peaches. No, I mean, that's, some people might, because they might really want peaches and they have the money to spend, but most of us are going to go, no, thank you. But when we go back 2 weeks later and they're on sale for $1.50 a pound, we'll buy a bunch of peaches, you know, if you like peaches or any other fruit, whatever. But when the price is high, the sales go down.
The higher price.
The lower the sales. Yeah. Okay. Here we have another scatter plot about the newspapers that are being sold versus the temperature outside. Do you see how these don't make any kind, they don't make the shape of a line? There's just a big blob of dots everywhere.
It's not a relationship?
Right. The dots do not approximate a line. So there's no relationship between the temperature outside and how many newspapers are sold. Which makes sense if you think about it. You wouldn't think the temperature would affect whether or not you wanted to read the news. But, you know, but now we can say mathematically there's definitely no relationship between temperature and newspaper sales. Okay. The technical term for the relationship between the number is a correlation. So when two sets of numbers or data have a relationship, It's called a correlation. And it can be positive or negative. And it can be strong or weak. Okay. Now the closer we see the dots to each other, the stronger the relationship is. If the dots are spread out, it's weak. If the dots are closer to being a line, it's strong. Okay, so we have a positive slope. So we're going up, that's why we have the positive. And then we have close together, and it's close to a line. Here we have a positive slope. And we can see that it's a line. Yeah, we can see that it's making a line, but they're spread out more. They're still in the right shape, but they're further apart. So that's why it's a weak correlation. So dots are further apart. But still line shaped.
The next one is going the opposite way.
So it's negative. Yeah, so we have a negative slope.
But it's together, so it's strong.
Yeah,
Wait, negative slope?
because they're going down.
Right, so if
Positive
it's
goes
starting
up.
if it's starting from the middle and going outwards, it's positive, but if it's starting from high and going down, it's negative,
Uh-huh.
even if it's not on the negative side?
Right. We're talking about slope,
Okay.
not. So positive slope is like when you're going up the mountain. Negative slope is when you're coming back down the mountain.
Okay.
So it's going to face down or face up.
Okay.
So that's what you want to
Going
look at.
down is negative, going up.
Yeah, so as you go from, like you're going to read a book, as you go from this side to this side, if it goes up, it's positive. If it goes down, it's negative. And again, if they're close together, like the dots are close together, you've got a strong correlation. And if they're spread out, you have a weak correlation, but they still need to be in the shape of the line. So like how these are all spread out, but they're not in the shape of a line.
Mhm.
Versus these are spread out, but they're still in that shape of a line. Okay? Everybody got this one? All right, now, no correlation can happen three ways. You can have random.
So the one that before the second slide was no correlation.
This one?
Yeah.
Yeah, no correlation because it's just a big blob. So we have no correlation if it's a big blob, like a random bunch. There's no pattern. And it does not look like a line. Okay? Or we can have what looks like a line. You see how this is kind of looking like the shape of a line, but it's a flat line. Okay? At this point, we have it's not random, but the values of the independent, so of the y, aren't really changing. Okay? So if the y's aren't really changing that much, then it doesn't matter what our x's are. So the x's aren't really affecting the y. The y is just whatever it is all the time. Does that make sense? So if they're not changing that much, if it's flat,
Horizontal.
yeah, horizontal, there's not a correlation. Okay. This is the slope is equal to 0 when you're flat. And likewise, if you're straight up and down, you're completely vertical. It's not random, and it looks like a line, but the x's aren't really changing. Yeah. And so if my x's aren't really changing, my x is always in the like 1 to 2 range, somewhere in there. It doesn't matter what the y is. If the x is not changing, then we don't have a relationship. X is just what it is.
If it's everywhere, if it's flat or if it's vertical, it's
Yeah.
not a correlation.
Yes. Okay, and this one is really easy. Everybody gets this one, no correlation, they're just scattered. But because these look like lines, they can be confusing. So if your line is vertical or your line is horizontal, there is no correlation. Okay? There's something called correlation, and there's something called causation. Yes. Correlation is when there's a relationship between two data sets. So we do get a line, and we can make predictions, right? The dots are close together. Causation is one thing is directly causing another thing. Okay? Now, just because there's a correlation does not mean that there's a cause. It doesn't mean that one thing is causing the other. Here's an example. If you, this is like a good example. If you look at the number of pirates in the oceans, and you look at global warming, as the number of pirates decreased, global warming increased.
Are you talking about modern day or?
Yeah, like if you go back in time and you're talking about pirates, like you do a long term, as the number of pirates went down, the temperature went up.
So the global change is the causation for the pirates?
No. I'm saying they have nothing to do with it. There is a correlation because the numbers do make a nice pattern. Pirate numbers went down as temperature went up. Like we get like a nice negative slope there. But that would, if there was causation, it would imply that pirates cool the world off.
Oh, okay.
Pirates have nothing to do with the temperature of the planet, right? We all can agree that pirates don't affect the temperature. Right, there's a correlation between the number of pirates and the temperature of the Earth. There is a correlation, but pirates are not causing the temperature, and the temperature is not causing pirates. There's not causation.
So what would be causation?
If you want to talk about temperature and like if you're up north where it makes a difference, ice cream sales.
The reason for a decrease in
Ice cream sales would be the lower temperature.
Whether it's the causation of the ice cream.
Yeah, because like you're not going to go out and buy ice cream and walk around in the park with ice cream in Boston in December. It's too cold. So ice cream sales go down. Yeah, so ice cream sales do go down in the winter. I mean, they don't flatten completely, but they do go down because people are not out walking around in the heat want some ice cream. Yeah. So that is causation. The temperature causes the decrease in ice cream sales. Do you see what I mean? That there's a difference there. So just because when we're looking at things and we're saying, oh yeah, those are related, that's a correlation, it doesn't mean one of them's causing the other. It just means that their numbers are working together nicely.
So the causation.
Yeah. Causation is when one thing directly causes another.
Okay.
Okay. So you get a higher allowance, it causes you to go shopping more.
Higher allowance, you spend less money.
No, higher allowance, you spend more money, right?
You spend more money, but then you have less money at the end of the day.
Well, yeah. But that's what I'm saying. You have a higher allowance, you're going to spend more money.
Yeah.
You have a lower allowance, you're going to spend less money. That's a causation. But if you increase your allowance, you're going to walk more.
No.
Maybe not. You know, like there would be a causation there.
Yeah.
Okay, does that make sense? Even if the numbers matched up, it didn't cause each other. Yeah.
We walk around the mall.
Well, maybe if you go to the mall.
See, that's how I think about math. Like, I think of a possibility. Would be the more.
So we talked about that if there's a correlation, it looks like the shape of a line, right? So the line of best fit is when you draw a line through your scatter plot. That closely as possible approximates the shape of the data. Okay? You want your dots to be equally spaced as much as possible around the line. Okay, these are not exact. It's called a line of best fit because it's the best line that you can create for the data. It's not a perfect line. Your line of best fit may not be the same as my line of best fit. You're eyeballing it, okay? It's not exact. It's the best approximation you can do. So if I have my scatter plot, okay, and I have some data and it looks like a line, you know, I'm going to come in here and I'm going to draw a line, probably, no, that's going to be too low. Probably about like that. Because to me, that line seems pretty evenly distributed between the dots. And then this line is what can be used to make predictions.
So that line is what we call the best fit.
Yeah. Yeah, this is the best fit line. And you mean like maybe somebody draws a line a little bit lower over here, or maybe a little bit higher. You know, you're trying to look at it the best as you can. Yeah, you want it to be as evenly spaced inside the dots, and you want it to be the same kind of shape as the general pattern of the dots. It's not going to be perfect. Plot, we have m and n. It says m is the independent variable. That anytime you see independent variable, that means that's the x. So this is going to be my x-axis, and this is going to be my y-axis. Okay, so my point is 4, 5. So I'm going to count these out by 5s real quick, just because it's easier to. So I've got my scale 1 by 1s. So my first point is 4, 5. So I start at 4, and I go up to 5. My next point is 9, 3, 9, 3, and then 13, 13, 11, and then 16, 18, okay, and then 17, 6. Yes, I have graph paper. 6, 11, 7, 18, 18, 12, there, and then 10, 16. Right. Describe the correlation. Perfect. New correlation. Okay. Could I have figured that out with these list of numbers? Maybe. But it's much easier looking at the picture. Huh? Because I